Hello, everyone. I'm Zhang from Xiusi. Today, I would like to introduce our work, Hierarchical Metadata-Aware Document Categorization under Weak Supervision. This is a joint work with Xiusi, Meng, and Professor Jiawei. So, to introduce the background, the task of this paper is hierarchical text categorization. As we all know, hierarchical structures are pervasive on the web. We give several examples here, including the Amazon product catalog and the archive paper category taxonomy. So the task of hierarchical text categorization is to automatically infer the category of a document into a given label hierarchy. Although recent studies on hierarchy-aware deep neural models, for example HMCN, and pre-trained language models, for example BERT, greatly improve the performance of hierarchical text categorization, they are less concerned with two challenges in real scenarios. The first one is limited training data. As we all know, these deep neural models are all training data hungry. However, to obtain a large training set is expensive because annotations need domain expertise, for example, archive papers and GitHub repositories. So in these scenarios, one may only expect very few training samples for each category. The second challenge is heterogeneous signals. We know that documents on the web are usually beyond plain text sequences. They're usually accompanied by metadata. Also, since we are doing hierarchical text categorization, we have the label hierarchy information, which reflects label intercorrelation. For example, if we are doing classification on the archive hierarchy, we know that computer vision is closer to machine learning than to chemical physics. So to summarize, we have these two kinds of information. Some metadata are strong topic indicators. Meanwhile, the hierarchy reflects label dependencies and intercorrelation. I will give several examples here. In the GitHub repository example, we have the label hierarchy, the paper with code task taxonomy. And the metadata of each repository is its user, the user creating this repository and its tags. And for the archive paper example, we have the archive category taxonomy as the hierarchy, and its metadata includes the authors. In the Amazon review example, the label hierarchy is Amazon product catalog, and its metadata includes the user and the product information. So now the question becomes how to jointly leverage hierarchy, metadata, and text in hierarchical text categorization. So based on the explanations in previous slides, we define our problem as follows. So the input of our task is a collection of unlabeled documents and the label hierarchy. Here we assume the hierarchy is a tree. So if in some cases the hierarchy has a DAG structure, we can simply follow a previous study and convert it to a tree by distinguishing each label node as a single pass node. Also, for each leaf category, we have a small set of labeled documents, for example, 5 documents. And each document, no matter labeled or unlabeled, is associated with its text sequence and metadata instances. So the task here is to predict the categories of each unlabeled document, and the labels should form a path in the hierarchy. To solve this problem, we propose our HIMCAT framework. To give an overview of the framework, we try to address two challenges as mentioned in previous slides. So the first one, to exploit heterogeneous signals, we try to jointly embed labels, text, and metadata into the same space. Here, because we have the hierarchy, we need to preserve the tree structure of the hierarchy in the embedding space. And second, to overcome the limited training data challenge, we propose to synthesize training samples to augment the original small-scale training set. To facilitate these two goals, we propose a hierarchical generative process to model category dependencies, metadata information, and textual semantics. To be specific, if we would like to do embedding learning, we can maximize the likelihood of the hierarchical generative process. This will yield an embedding learning objective. And if we would like to do data augmentation, we can simply follow the hierarchical process, which allows us to synthesize training samples. So now I will introduce this hierarchical generative process in details. The process is illustrated in the right figure. It has three main steps. In the first step, the embedding of the child label will be generated by the embedding of its parent label. The intuition here is that given the label hierarchy, the semantics of a child label should largely depend on its parent. So inspired by the softmax function, we define the conditional probability as follows. So the probability of the child embedding given the parent embedding should be proportional to the exponential of their inner product. However, we cannot fully borrow the softmax function here because we are defining a continuous distribution of an embedding vector. However, softmax function describes a choice among a finite number of candidates. So instead of using the softmax function, we use the VMF distribution. We can see its mathematical definition here, and it also satisfies this property. And we can see that with this generative probability, the label embedding can be generated in a top-down manner. We start from the root node and repeat the process until we reach the leaves. And after we getting the embedding of the leaf labels, we can have the following two steps. In step 2, we can use the embedding of the leaf label and the embedding of the metadata to generate the embedding of the document. And in the third step, we can use the document embedding to generate word embeddings one by one. And the conditional probabilities are very similar to that in step 1, so I just omit them. Now, with this generative process, the question becomes how to use it in our framework. So here, our HIMCAT framework has two key modules, the Joint Representation Learning module and the Hierarchical Data Augmentation module. Both of them are guided by the hierarchical generative process. To be specific, when we do joint representation learning, we can treat the embeddings of all the labels, words, documents, and metadata instances as the parameters of the generative process. And then we can simply do maximum likelihood estimation of the parameters when observing the corpus, including the hierarchy, the metadata, and the text. When we want to do hierarchical data augmentation, after the representation learning, we have this embedding space, and we can just follow the generative process to synthesize training data for each class. And then, based on the augmented training data, we can train a hierarchical classifier. Now we will not be worried about the overfitting problem or the label scarcity. We simply adopt the top-down training strategy that classifies documents at the top layer and then propagates the results to the next layer until the leaves. For each non-leaf category, we need a flat classifier to classify the documents to its child categories. Here we adopt the classical convolutional neural network structure proposed by Kim. And also, we would like to mention that embeddings trained in the joint representation learning step can be used as the initialized embeddings of the input layer. So that's all for our HIMCAT framework. Now we would like to present our experimental findings. We use 3 data sets from different domains in our experiments, including GitHub repositories, archive papers, and Amazon reviews. I think I have introduced them in previous slides. And to follow the weekly supervised setting, we use 5 training documents for each leaf class. This table shows the dataset statistics. Okay, so here is the performance. We repeat each experiment 3 times with the mean performance reported. And also we conduct a significance test and report the p-values. We can see that HIMCAT consistently outperforms the compared baseline methods on all 3 datasets. In most cases, the performance gap is statistically significant. And second, HiMCAT outperforms better than Hierarchical class and MetaCat. Here, MetaCat is a baseline that does not use any hierarchy information. Hierarchical class instead is a hierarchical text classification method, but it does not incorporate the hierarchy into embedding learning. So this observation indicates the importance of considering label hierarchy and incorporating it into representation learning. If we check another baseline BERT, we can see that despite the great success of BERT in many supervised NLP tasks, it does not perform well in our problem settings. There may be two possible reasons. First, directly using BERT for text classification does not consider metadata and hierarchy information. Second, the small set of training data may not be enough to fine-tune BERT. Okay, so our HiMCAT framework has two key modules, representation learning and data augmentation. Now we check their contributions separately through ablation studies. We first present the ablation study of representation learning. Here we can have the following ablations. The no hierarchy method does not consider parent-child relationships in representation learning. All the other modules are identical to our full model. And no metadata does not consider metadata document relationships in representation learning. Moreover, instead of ignoring all metadata instances, we can overlook one specific type. This will yield ablations including no user, no tag, and no product. So we can see that HiMCAT, the full model, still performs the best, which means that both metadata and hierarchy plays a positive role in the classification process. And also the contribution of metadata is larger than that of the label hierarchy, possibly because metadata information is denser than hierarchy information. Here by denser, I mean that each document has its own metadata, but the whole dataset only has one hierarchy. For the data augmentation module, in all previous studies, we use 500 synthesized documents for each category. Now we can vary the number from 0 to 2000. Here is the performance plot. We can see that when we compare 500 synthesized documents with 0, the average absolute improvement of the overall F1 scores on the 3 datasets is 21%, which means data augmentation can mitigate label scarcity. However, when we have more synthesized training documents, for example, we compare 2000 ones with 500 ones, the average absolute improvement becomes 0.1%. Actually, the performance starts to fluctuate. Moreover, when we have more synthesized documents, the training process will be longer. So to strike a good balance, we believe 500 is a good choice here. Also, to give a case study on the embedding learning module, we visualize the embedding of the hierarchy here. We can see that the tree structure of the label hierarchy is well preserved in our embedding space. And more specifically, in the archive embedding space, the quantitative finance node is embedded near the root because it is an interdisciplinary area. And its children are embedded closer to math and physics than they are to CS and quantitative biology. This indicates that our joint representation learning module not only considers the label hierarchy, but also captures text semantics. So to conclude our work, we present HiMCAT, an embedding-based generative framework for hierarchical metadata-aware document categorization under weak supervision. The framework is featured by a joint hierarchy metadata text representation learning module and a hierarchical data augmentation module. And we propose a generative process to guide the design of both modules. Also, we observe a consistent improvement of HiMCAT over competitive baselines. So that's all for my presentation. If you have more questions, feel free to email us and also refer to the paper. Thank you.